guys, I hope you have done well on CSIR December 2019 Chemical Sciences, and I hope you are getting good score after checking your response sheet with CSIR challenging key. Here in this video, we are going to analyze each and every problem, why that particular answer is correct, and what is the concept involved in it. So watch the video completely to get best conceptual analysis of each and every problem and get vast information from each of it. So here, if you are interested, visit and join chemmasters.online for the best concept-oriented online courses. Now just come to the point of question. In IR spectrum recorded neat, a compound shows a strong broad band at 3300. The band becomes sharp and shifted to 3600 when the spectrum is recorded in CCl4 at high dilution. This proves that the compound has. So first thing, whenever we are going to solve the problem, we need to look at the information given it, okay, given in that particular problem. Yeah, here we have given with a compound IR frequency value that is 3300. So in general, 3300 belongs to alkyne hydrogen, and in other cases are also observed where the hydroxy functional group which is having hydrogen bonding will also show the value nearly 3300. Okay, that's why that means whenever you look at the given options, all the options may have the chances for the answer. Now we need to look at deep into the concept. That is here the second step, whenever the same compound recorded its IR spectrum in carbon tetrachloride at high dilution showing 3600, that is increased IR frequency value. Okay, right. Here, in general, OH functional group is having 3400 to 3700 frequency range whenever the hydroxy functional group is free in that particular compound without hydrogen bondings. Okay, right. It is simply just confirming us that, see here, terminal alkane group is absent in that particular group because terminal alkane group doesn't change or doesn't change with the change in that means dilution of that particular compound solution. Okay, right. And at the same time, OH group is confirmed here as a functional group which is in the particular compound. OH group present in severely sterically hindered environment. The steric environment or steric hindered environment is not going to affect the IR frequency here. Okay, so fourth option is also eliminated. Now the answer may be in first and second options. Just look at the first one, OH group which is involved in intramolecular hydrogen bonding. Okay, right, we need to look at intramolecular hydrogen bonding. Here, just take a compound with two OH functional groups. Here we can see hydrogen bonding. Okay, we may expect hydrogen bonding and we can call it as intramolecular hydrogen bonding. Okay, right. This compound, just consider if this compound is taken in carbon tetrachloride at a high dilution also, there will be no change in hydrogen bonding, that is intramolecular hydrogen bonding, because these functional groups are present on same compound. That's why the dilution doesn't affect hydrogen bonding. Okay, right. So whenever hydrogen bonding is not going to change on dilution, there will be no change its IR frequency. Okay, so here just remember that whenever hydrogen bonding is observed in a particular compound, the IR stretching frequency decreases. This is the simple fundamental concept we need to remember. Okay, so due to this hydrogen bonding, the value of OH frequency, IR frequency value is decreased to 3300, and it will be same at high dilution also because of intramolecular hydrogen bonding. Okay, so first option is eliminated. Now second option must be the correct answer. Now just try to check it. Here the compound X with OH functional group, here other same compound with functional group OH, and we may expect intermolecular hydrogen bonding. Whenever if we take this particular compound in carbon tetrachloride at high dilution, then the compounds will be far away from each other. Okay, in that condition the hydrogen bonding will be minimized, and at high dilution we can expect there will be no hydrogen bondings. Okay, so whenever hydrogen bondings are absent, the functional group OH will be free, and which will show its IR stretching frequency in the range of 3400 to 3700. Okay, so here 3600. So here the increasing value at high dilution, increasing IR stretching frequency of that OH in high dilution is due to intermolecular hydrogen bonding, which is cleaved at high dilution. Okay, so second option is our answer. Next question. The major product found in the following reaction is, just look at the substrate. Here we have given with 1,2 disubstituted cyclohexane. Okay, so 1,2 groups are trans to each other. So whenever we are given with cyclohexanes in the particular reactions, we need to look at their chair conformations for the proper mechanism to give correct answer. Okay, just remember this point. Now, so just try to check its chair conformation. So 1,2 trans groups on cyclohexane will move into axial or equatorial in its chair conformation. Okay, so we may expect two conformations of that cyclohexane, 1,2 trans dibromocyclohexane. One is axial, okay, and another one is equatorial. Okay, right. And here I'm asking you a question, that is, which conformation is stable, first one or second one? Try to answer. Okay, right. Now just come to the point of potassium tertiary butoxide. We know that potassium tertiary butoxide is a bulk base. Okay, so due to its bulkiness, in majority of the cases potassium tertiary butoxide act as base and always try to abstract acidic protons. Okay, right. And in rare cases, potassium tertiary butoxide can act as a nucleophile where steric repulsions are completely minimized. Okay, but here just look at the substrate. The two bulkiest bulk bromine groups are there at 1,2 positions. Okay, so steric repulsions are common. That's why nucleophilic attack is not the favored case here. So potassium tertiary butoxide can act as base in the given reaction conditions. Okay, right. So we can eliminate fourth option and third option from the answers, because here we can see nucleophilic additions or nucleophilic attack of that particular potassium tertiary butoxide. Now just look at the basic nature of potassium tertiary butoxide. Whenever it is going to abstract acidic proton, the eliminating groups must be trans to each other. So here just take X and Y. These two are eliminating group. They must be opposite to each other or 180 degrees apart from each other. Then only that elimination is possible, and we can call it as anti-elimination. Okay, right. Now just look at these two conformations. Here we can take axial substituted or simply axial conformation. So where you can get the best explanation for it. Here equatorial and one is axial. Okay, just say axial here. Right. So whenever base abstract this proton, because here hydrogen, that is axial hydrogen, and here axial bromine, which are 180 degrees apart from each other. Okay, so here the bond cleavage takes place and loss of HBr takes place and formation of a new double bond here. And here we have hydrogen, and here we have another bromine, and base again attack on this axial hydrogen and cleavage takes place, and here is the formation of new bond here, and here we have double bond. Just convert this cyclohexane chain conformation into its planar form. So simply you will get this. So second option is the correct answer. Okay, right. And next question. Just look at the figure. The Miller index for the plane as shown in the figure and parallel to the C axis is. Here we have given with the coordinates A and B in this way. Okay, so just try to take those coordinates. So here we have A, and here we have B, and C must be here. Okay, right. I'm trying to develop a unit cell here. Okay, right. Here is the unit cell. Now, so I'm just developing a unit cell. Right. Now, after developing it, here we have plane, right? So here we can take a plane like this from that figure, right? After taking this figure, we need to look at recipe, that means intersects on each of the axis A, B, C, right? Just look at here, origin from that point, and the plane here intersecting onto that A, origin of A, okay, axis of A. So we can take the value 1 for it. Now the second step, look at the axis B, where the plane is intersecting on the B axis, completely half of it. Okay, so just make it perfect cube here, and if you do that, so the plane is completely just intersecting on the half of that axis B of that particular unit cell. That's why we can take half here. And just look at the axis C, the plane is never intersecting on this axis, simply it is moving parallel whenever the axis is simply moving. Okay, so that's why we can take infinity here, and by just taking reciprocals we can get the Miller indices 1, 2, 0. Okay, so here just take it 1, 2, 0, and second option is our answer. To get the best concept on Miller indices, just visit and join on chemmasters.online. Okay, right, now just come to the point of next question. The major product found in the following reaction is, just look at the substrate, and here we have given with TFA, trifluoroacetic acid. Okay, so just look at the substrate, and by just looking at the substrate and TFA, we can say that we are going to do cleavage of protecting groups of functional groups COOH and NH2. Okay, right, just expand the protecting groups. Just remember my words. Whenever we are given with shortcut forms of functional groups and any protecting groups, so just try to expand their structures. In that case, you will get an idea how the mechanism will take place. Okay, you will not get confusion whenever you expand those functional groups and protecting groups. Okay, right, C double bond O CH2 and here PH. Right, whenever we apply TFA on it, so here just take TFA here. Whenever TFA is there in reaction conditions, which produces more number of simply more number of protons. Okay, CF3 here, right? And we have two oxygens with lone pair of electrons. Here I am asking you one question. Which lone pair of electrons, that means the lone pair of electrons on which oxygen, that is simple heteroatomic oxygen or carbonyl oxygen going to attack on proton which comes from the TFA. Okay, so here just look at the lone pair of electrons on this oxygen involves in stabilization of this carbonyl oxygen. That's why these electrons are not free. Then the lone pair of electrons on carbonyl oxygen attack on proton which comes from the TFA. Okay, right, and here just wait for it. C double bond O H, and here O. Here we have butyl group, tertiary butyl group, and we can take that means hydrogens here, right? And here we have oxygen with positive charge. More electronegative oxygen is with the positive charge. That's try to get its electrons back. Okay, so here driving force is simply CF3. C double bond O minus acting as base which abstract this proton. Okay, and bond cleaves here, and double bond goes on to oxygen to compensate the positive charge, right? And in that case we simply get C double bond OOH. Okay, that is the formation of carboxylic functional group. Right, now just look at NCBZ. So here TFA is not the best reagent, but the best reagent is H2 palladium catalyst, that is OH2 hydroxy group, right? Why? H2 palladium is the best reagent here, and we can call it as hydrogenolysis. Okay, just take it, hydrogenolysis. So just look at how it is the best reagent. Now just take it, NH, C double bond O, CH2, PH. Okay, right. In the first step, palladium catalyst takes other means the organic group or organic substrate gets oxidative addition onto palladium catalyst. So the lone pair of electrons on oxygen attack on palladium, palladium going to attack on CH2. That's why here is the formation of C double bond O, palladium, CH2, PH, and here two hydroxy groups. Okay, here oxidative addition takes place. In the next step, by the loss of two OH groups and addition of hydrogens. Okay, so simply we can take C double bond O and O palladium, here CH2PH. Okay, here two hydrogens. Now the reductive elimination takes place here. Okay, so just look at here, reductive elimination onto the palladium here. So the bond cleaves here, and bond, that means electrons comes onto nitrogen, and here in this reductive elimination, elimination of carbon dioxide takes place and addition of hydroxy groups, regeneration of palladium catalyst, and here is the formation of NH2 functional group. Okay, so the best reagent here, H2 palladium catalyst, that is hydrogenolysis, is the best case to deprotect that NH2 from that CBZ. Okay, right, and that's why here we can say TFA is going to deprotect this carboxylic functional group only, not that NCBZ. Okay, for example, here TFA is going to attack on NH2CBZ. What happens? Here is a formation of here you can see isobutene, right, in that particular reaction. Right here, whenever the lone pair of electrons, just look at the oxygen with lone pair of electrons, which is going to attack on proton, which comes from the TFA. Here we have the competition for the stabilization of carbonyl oxygen from the lone pair of electrons on nitrogen and lone pair of electrons on oxygen. Okay, so that's why, so the lone pair of electrons on oxygen or just having less intensity to stabilize this carbonyl group. Okay, and at the same time, so the lone pair of electrons on oxygen, the heteroatomic oxygen, or freely attack on proton. Right, in the next step, cleavage should be takes place here. Right, and as we seen, the formation of base CF3 C double bond O minus, which is the strong conjugate base of trifluoroestic acid. Okay, so which is going to abstract proton from that pH, but it is not possible because here we have already double bond is there. It is not going to produce triple bond on that benzene ring. So TFA is not simply react with this NHCBZ. Okay, so that's why only TFA reacts with this carboxylic acid producing group, and which cleaves it to produce COOH. Okay, and that's why just look at the options. Only COOH, that means carboxylic group is deprotected, and NHCBZ will be there, and methoxy group will be there. So option 4 is the correct answer. Okay, right, and at the same time, so if we are having BOC, the same protecting group here, that is, just take it, NH BOC, that is tertiary butyl carboxymate. So just take it, and if we have this, trifluoroestic acid is going to react with it to deprotect this amine functional group. How? As we seen for that carboxylic acid deprotection mechanism. So simply here also the lone pair of electrons on nitrogen and lone pair of electrons on oxygen are in competition. Okay, so that's why the electrons on oxygen are somewhat free, right? And in the next case, we can also consider the steric factor, that is C double bond O. Here just try to take oxygen, and here we have hydrogens. CH3. Okay, right. Steric repulsions can be seen from this lone pair of electrons on carbonyl oxygen. Both these cases simply drive the lone pair of electrons on this heteroatom to attack on proton. Okay, so that's why after attacking it, the cleavage is possible. That is, hydrogen cleaves here, formation of isobutene, and the elimination of carbon dioxide takes place, and formation of NH2. So what you understand from this? Simply, if NH is protected with BOC, then which is also going to react with TFA. But here NH is protected with CBZ, so CBZ is not going to react with TFA, but which is going to react with hydrogen H2 palladium. Okay, so option 4 is the correct answer. So here I'm just giving the extra information. I hope it will be helpful for you. Yeah, next question. For the complex shown below, in non-flexional state, the expected P31 HNMR resonance is. So just look at this point. This is the information we need to look at. Non-flexional. So these are not just exchanging their positions or not just moving. Okay, right. So simply they are in different environment. Okay. So here you can see this is the environment. Okay. So these two are in different environments. Sorry, here we have phosphorus here and phosphorus here. That's why these two phosphorus are in different chemical environments from this that means axial group, different axial group, and different equatorial CO ligands. Okay, so that's why each of these phosphorus can produce N+1 resonance. That is simply doublet, because here we have one phosphorus. Okay, so 1 + 1 2. So simply doublet here from this phosphorus and doublet here from this phosphorus. So we can expect 2 doublets. So option 4 is the correct answer. Okay, right. Thank you very much. And if you're interested, just visit and join chemmasters.online for the best concept-oriented online courses on chemistry. So in the next lectures, we are going to discuss all the questions. Right. Thank you very much.